Okay. Okay, welcome to this lecture of 7th of December 2016. Hopefully you're doing okay studying for the for Chapter 3 quiz, which will be on Monday. Hopefully you're doing... Okay, just check the sound there. Okay, so last time we were studying the roots of polynomials, in particular the different ways of finding roots, or seeing how many roots you actually had, whether they're positive or negative, how many of each kind you might have. And this particular last thing I think we studied was Descartes' rule of signs. Descartes' rule of signs. And we looked at, I gave you these exercises to do, which I was going to go over. The bakery problem, that's basically done in the textbook, so that's not too hard. But some of these are a little more difficult and tricky, like this one, and so I wanted to go through these in more detail. Okay, so let me just bring up that part of the chapter 5. Section 5.5. Okay, so let's see here. So number 6 says, for the following exercises, use the remainder theorem to find the remainder. So you have x to the 4th minus 9x squared plus 14 divided by x minus 2. And we're up to our own resources. It just says use the remainder theorem, or yeah, okay. So use the remainder theorem. And we just has to find the remainder. So this is just a simple matter of using the method of synthetic division. Okay, so we just set up our coefficients here in a row. The first one is 1 for x to the 4th, and then 0 for the next term because it's x cubed, it's not there. And minus 9 for x squared, 0 for x, and 14 for the constant term. And then, in order to do synthetic division, you just put in the number that's being subtracted from x, namely 2. And then you take down the coefficient. 2 times 1 is 2, times plus 0 is 2, times 2 is 4, plus minus 9 is minus 5, times 2 is minus 10, plus 0 is minus 10, minus 20, plus 14 is minus 6. So that's our remainder. Okay, so that's a very straightforward application of the remainder theorem. Remember, which says that evaluating the polynomial at a real number k is equivalent to first dividing the polynomial by x minus k, getting a quotient and a remainder, when you set x is equal to, so this is what's true in general. This is what you get for a polynomial by dividing by x minus k. You get the quotient and the remainder. But then when you take f of x is equal to k in that expression, this term goes away and you just get r. So that enables you to find the remainder right away by basically evaluating the function at x equals 2, which synthetic division does as well. All right. Alternatively, you could just plug in x equals 2 here or here. So you could just find the remainder that way, and that will give you x to the 4th, which is 16, minus 9x squared is 2 squared plus 14. 16, right, plus 14 minus 9 times 4, 4 times 9, 36. And you can see that's 30 minus 36, which is also minus 6. So that's another way to do it. Just plug in the number, get the evaluation of the function at k equals minus 6, and then that's, or at k equals 2, and immediately that gives you the answer. Okay. Number 11. Use remainder. Use the remainder theorem to find the remainder obtained by dividing x to the 4th minus 1 divided by x minus 4. Okay, so here, which method? Okay, so here are the two polynomials, number 11. Okay. So which method would be simpler in this case? Well, you have a high power of x here, and so you'll have a long row if you used synthetic division. Right. So synthetic division often is a useful way to do it, but in some cases synthetic division might be unwieldy or intractable. Okay, so that means try the other method. This is simply the plug-in method. Plug it into the original function. Not really a method. It's just plug it in and evaluate the function at x equals 4, right? So for this is our function, just plug in x equals 4. So it's even simpler than the synthetic division method in this case because you only have one term. So you evaluate 4 to the power 4 and then subtract 1, and lo and behold, that's 4 squared is 16. 16 squared is 256. Minus 1 is 255. Okay, so if you chose to do it the other way, then go ahead and do that by all means. You'll get the same answer. You should get the same answer as this. In fact, I did try it and I did get the same answer by doing it the other way as well. Okay. Number 21. Okay, so please do examples like this. It will help to sharpen your skills. It will help to make things more clear as you encounter, the practical issues of solving these problems. Okay, the objectives are, not just to understand the terminology used, but to use these methods to solve real-world problems that you might have when you work in a job involving math problems. So number 21, use the factor theorem to find all the real zeros for a given polynomial function and one factor. So you're given a polynomial, you're given a factor. Let's see. So let's see what the polynomial is. Number 21. And they give you the factor. Okay, so 2x cubed plus 5x squared minus 12x minus 30. Sorry, minus 12x minus 30. And the factor that we have is 2x plus 5. Okay, so notice we're actually using one of the possible rational roots. So remember what the rational roots are. They are any factor of 30 divided by any factor of 2. Right? So those would be the factors of 30, which will be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, plus or minus 30. There are how many factors of 30? You have 2 times 3 times 5 is 30, so it's 2 times 2 times 2 is 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So there are 8 factors of 30. Each gets a plus or minus sign. And then you divide the odd factors only by 2, because those will give you new ones. So these are all the possible rational roots. So 1/2 plus or minus 3 over 2, plus or minus 5 over 2, and plus or minus 15 over 2 would be all of them. And the rest are odd, so they'll just give you integers which have already been included. Okay, so these are all the possible rational roots. So this root this factor represents a root of what? Right. Minus 5 over 2, right? So it's over here. So we're going to check to see if that indeed is a factor, and then we'll find what the other factors are. So here we go. So we put in the coefficients in our row. 2, 5, minus 12, and minus 30. And we put our rational root minus 5 over 2 in here. So we bring down the 2, multiply, get minus 5, and then add, get 0. Okay, multiply, get 0, add minus 12. Multiply, we get 2 cancels here, and you get 6. 6 times 5 is 30, and I get a plus sign. 30 minus 30 is 0. Okay, so we do, in fact, get 0. And what's left over is this polynomial represented by these coefficients. So it's 1 degree less than this, which is x squared. So 2x squared minus 12. And the other factor is actually x plus 5 over 2. So the 2 actually has been taken out of this factor, right? And it's simply been moved actually over here. So if you factor out the 2 from here, you can put it back over here. right, so you can check, verify that this is indeed equal to the original polynomial. Yeah, factoring, probably grouping, factoring by grouping also will do it for you. And so we get that the rest of the factors are, just take the roots of this factor, and so it's x is plus or minus square root of 6. So the complete factorization of this polynomial is x plus root 6, x minus root 6, 2x plus 5. Okay, and so the real zeros are x's, so plus or minus 6 and minus 5 over 2. I'm trying to write them in increasing order. I think this one is larger in absolute value than this one, so this is more negative than this. Okay, so those are my real roots. Maybe we can check this with Descartes' rule of signs. How many changes of sign are there for this polynomial as it is written? None, and then one change of sign. So that means there's one positive real root. Okay, so that works. And then f of minus x is just change the sign of this term and this term, and I get minus 2x cubed plus 5x squared plus 12x minus 30. So I get one here I get a change, and then here I get a change. So that's two changes of sign. And so the number of negative roots is either 2 or 0. And we do get 2. So that works as well. So that's in agreement with Descartes' rule of signs. All right. Now what is the next one we're doing? 21 and then 22. Use the rational zero theorem to find all the real zeros. Okay, so in this one, of course, I didn't have to do the explicit enumeration or listing of all the rational zeros here, which I'm erasing. But I just did that to illustrate that if you do find a rational root, then it must have that property that it's a factor of the constant term divided by a factor of the leading coefficient. Okay, so number 22 is to see its explicit question. For the following exercises use a rational zero theorem to find all real zeros. So it's x cubed minus 3x squared minus 10 x plus 24. Equals 0. So this one is a little bit simpler in that you only have to consider the rational roots or the factors of 24. So the factors of 24 is equal to, in its prime factorization, it's 3 times 8, and 8 is 2 raised to the power 3. So 2 to the power 3 times 3. So all of the factors, how many factors are there altogether? You just take this exponent, add 1, so it's and multiply by this exponent, add 1. 4 times 2. There are 8 factors altogether. So let's list them. So you include 1 and 24. 1 and then 2. 3 is a factor. It's easier to actually look at this and then determine. 4 is a factor. 5 is not. 6 is a factor. 7 not. 8 is a factor. 9 is not. 10 no. 11 no. 12 yes. And then the next one would be going all the way up to 24. You check it 1, 2, 3, 4, 5, 6, 7, 8. So that includes all of them. So we're done. Okay, another way to do this, I like to show this in my math, I just like to show it in my math 101, is you take 24 and you express it as a product of two numbers starting with 1. You start with the smallest number that divides into it. It's always going to be 1. And the other factor is 24. And then you just go up to the next prime, or the next number. It doesn't have to be prime, but in this case will be 2. 2 divides into 24, so you can write this as 2 times 12. And then 3 times 8. 4 times 6. And, well, you can't go any higher without starting to repeat factors. The next one you'll get 6 times 4. But that's just this back going the other way. And the next one is 8 times 3, 12 times 2, 24 times 1. Now you don't have to worry about missing any factors in here. None of these can be possible factors, because if they were possible factors, then we'd have another factor over here, which is between these two. And we're pretty sure we didn't miss any on this row. In fact, it's just all consecutive integers here, 1, 2, 3, 4. So there's nothing in between them. Therefore, there's no factors in between here. No factors are missing here. So that's another way to do it, and you just go 1, 2, 3. You just go like this. So that's another way to kind of an easy way to basically list all of the possible factors of a number without missing any. But anyway, it does help to know how many factors there are, so you can always count them and check them afterward. So we list the possible factors of 24, and then put a plus or minus sign in front of all of them. Right. Be explicit as possible, as much as possible, and then you write down the coefficients, and go ahead, start plugging in and guessing, trying to check to see if these give you 0 in the end here, in which case you'll have a root. So 1 minus 2 minus 10 is minus 12, minus 24 is 12. It's not 0. Let's try minus 1. So 1, minus 1 is minus 4, plus 4 minus 6, plus 6, 30. No. Okay, let's try going up to 2. Well, 0. 0 is always easy because it's just this row. You start with 1. 1 times 0 is 0, and you just add the coefficient to 0, add the coefficient to 0, add the coefficient to 0. Okay, that's obviously not going to be 0. Then you try 2. 1 times 2 is 2, minus 1, minus 3 is minus 1. Minus 2, minus 10 is minus 12, and then we get minus 24. Okay, there we go. All right, and now basically this will simplify the problem so much that we don't have to go any further. We don't have to check any further roots. Okay, so we have a rational root here. Okay, we have the remaining coefficients of the quotient polynomial here. So x squared minus x minus 12. And then let's try factoring that. Well, that can be done using our Math 101 methods. It's just x minus 4, x plus 3. And you can check minus 4 plus 3 is minus 1. 3 times minus 4 is minus 12. We're done. All right. Explicitly, if you wanted to check this out one more time, you can just simply expand it. X cubed minus 2 minus 1 is minus 3x squared. And then minus 12x plus 2x is minus 10x plus 24. Yeah, it's the same as before. Okay. So the three roots are 2, minus 3, and 4. Okay. All real. Does it work with Descartes' rule of signs? We can quickly check that. How many changes of sign are there the way it is? 1, 2. I guess we have 2 positive real roots. We change the sign of x cubed and minus 10x, and we get minus, minus, plus, plus. So there's just one change, and we do have one negative real root. So Descartes kind of confirms that this is fine. All right. Finally, number 39. Okay, so number 39 is another example of this kind of thing where you list all the possible rational roots. Okay, and of course not all of them can possibly be roots because there are too many. You can only have at most 3 real roots, so of course not all of those will be rational. In this case, 3 of them are. 3 of the numbers from here are the 3 rational roots. Okay. So number 39 says, again, 8x to the 4th plus 26, x cubed plus 39, x squared plus 26x plus 6. Use the rational zero theorem to find all the real zeros. Okay, so I'll just put the coefficients down. We have a 1, 2, 3, 4th degree polynomial. And we look at the leading coefficient and the final constant term. So called A0. And look at the factors of the latter and divide them by the factors of the former. Okay, so I'll head right into the actual calculations by putting down the coefficients in synthetic division. Okay. By the way, what does Descartes' rule of signs say? Descartes says, how many positive real roots are there? None, because there are no changes of sign as it is written. No positive real roots means we can simply not consider positive real roots. Right? And now that's obvious, because if we put a positive number here, we'll just get positives all the way down. We're not going to decrease it at all. Okay, so we'll just consider the negative roots here, negative possible roots. So the final coefficient is 6. So the possible factors are then minus 1, minus 2, minus 3, minus 6. We have 6 is 2 times 3. So that means it's 2 times 2 is 4 factors. There we have them. And then we can divide by, well, we can divide by the odds by 2. We can divide the odds by 4. We could divide the even by 4 as well, but we'll just get 1/2 and -1/2 and -3/2, which we already have here, by divided by 2. And we could divide them by 8. So this gives us all possible rational roots that could be solutions. All right. So, and then I should have written it somewhere else because I want to write each evaluation in one line. I'll just go down the list. So what do I get? So I got 1, and I'm going to be a little bit observant of what's going on when I decrease. Remember, I'll start at -1, and I'll decrease, go larger and larger negative. And I might miss some because I'm skipping the rational roots for now. So let's see what I get here. -1 times 8 is 8. Sorry, -8 plus 26 is 18. -18, subtract from this, 21. Subtract from this, I get 5. Subtract from this, I get 1. Okay, now let's make it a bigger negative, -2. 8. So I don't get a root there. -8, -16, plus 10. -20, plus 19. -38, get -12, that's 24 plus 6, 30. Okay, so for, this is what I got before. Okay, now what I'm doing is I'm watching changes in sign here, because eventually I should get if I go large enough negative, I should just get alternating signs here. Plus, it should be minus, plus, this should be minus, and then I'll get a plus here. If I get any roots at all, I'll see them, I might be able to catch them with a change of sign between sequential roots, sequential evaluations. So let's try them. Let's keep going. -24 plus 2. -6 is 33. -99. I had -99 plus 26 is -73. And this is going to be, okay, that's overwhelmingly big. It's not going to vanish. So 219 plus 6, 225. And finally, let's try -6. 8 minus 48. Okay, now we have a minus sign here, and that will be -22. Okay, it's going to get big now again, and so that's 132 plus that, it's 139 is 171. And 6 times that is a negative sign. 42, 1026. And minus, it's going to be a negative sign, and a plus 26 is actually going to give us -1,000, which is a nice round number, but it doesn't really mean anything here because, anyway, this is 6,000 plus 6. So it doesn't vanish. Okay, so let's try our fractional roots here. We can skip the positives, just look at the negatives. So -1/2 gives us 8. -4, 22. Divided by, I get -11. 39 minus 11 is 28. We want to get even numbers after the subtraction because we want the next division by 2 to give us an integer. So this is working out so far. -14 plus 26 is 12, and then, okay, here we go. minus 6 plus 6 is 0. So here's our rational root, our first one. And well, let's now use these coefficients as our new polynomial. So this will be an x cubed polynomial. And we want to, so this will have the same possible rational roots, except we've already eliminated these four. Let's try this one again, because minus 1 over 2 could be a repeated root. Oops, minus 1 over 2. Let's try it, and we get 8 minus 4, 18, minus 9, 19. Okay, it's not going to work now, because we'll get a fraction here. Minus 19 over 2 plus 12, 24 minus 19 is 5 over 2. And this, by the way, this is terminating the polynomial division, because we don't have this. The last coefficient, this is a constant coefficient now. That's the last one. So we'll just go down this column right now, whereas we had this one before. Okay, so that's not 0. Let's try the next one, minus 3 over 2. 8 minus 4 times 3 is minus 12. Go back up to here, minus 12 is 10. And then this is minus 15. Okay, we're going to get 13. Again, not 0. All right, and let's try the next one, minus 1/4. So we get 8 minus 2 is 20, minus 5, 23. No, it's not going to give us an even fraction. How about minus, which that should be 3 over 4. Minus 3 over 4. We get 8 minus 6 is get 16, and then we get minus 12, which is 28 minus 12, 16. Then we get 4 cancels, and we get 4 times 3 minus 12 is 0. Yes. Okay, so the two rational factors are this one and this one. So that was a bit of a tricky one. And then what is remaining here is this quadratic. This one has a quadratic coefficient, or quadratic form. So writing it all as one thing, one factorization, the original polynomial with these coefficients was 8x fourth plus 26x cubed plus 39x squared plus 26x plus 6. So that's equal to these factors, x plus 1/2, x plus 3/4, and the remaining part, which is 8x squared plus 16x plus 16. Okay, so notice I have the factors of 2 and 4 in the denominator here, and I can put those together and get 8, and simply write this. So I multiply everything by 2 here and by 4 here, and I divide by 2 and 4 in this. So what does that give me? Okay, in other words, I can take the 8 out of there, take the 8 out of this one, and multiply by these two, and I get these two factors. And then I take the 2 out of there and multiply that. Take the 4, that's the only remaining factor, and I get 4x plus 3. Finally, and so these are factors written in kind of the simplest form, namely in terms of integers, and there are all the common factors are taken out. Right? There's this factor of 8 that's been taken out and put in with these ones, and that makes them all integers. So that's all nice. There's no common factor overall in this whole equation, right? Or the polynomial that we started with. So possible rational roots, or the possible, all the roots are, oh sorry, all the zeros are minus a half, minus 3/4, and the roots of this, well, they'll be complex. So what will they be? You use a quadratic equation or complete the square. Remember we did this before. You put a 1 in with this group and you get a perfect square, x plus 1 squared, and then what it remains is another 1. So to make that equal to 0, you have to solve this equation. X squared is equal to minus 1, which requires the use of the complex number I, so we get plus or minus I. Right. And so x is equal to minus 1 plus or minus I are the two roots. So this factors into x plus 1 plus I x plus 1 minus I. If you desire to factor every expression. So these are the possible roots. These are all the roots. There are 4 of them. 2 of them are complex. The other 2 are real. Descartes' rule of signs says that how many sign changes would there be if we plugged in minus x? Well, this would change, so we get 1, 2, 3, 4. 4, 2, or 0 possible changes of are the changes of sign. So there are 4, 2, or 0 possible negative roots, and then we do have 2 negative roots. Okay. And these are not real, so they're not covered under Descartes' rule. And that's all for this exercises I wanted to do in this chapter. Okay. So, in the following chapter, we'll deal now with rational functions. So rational functions are functions which have a polynomial in the numerator and also a polynomial in the denominator. Going to re-plug this back in. The board might not be secure there. Okay, and so let's get into that. So rational functions are simply a ratio of 2 polynomials, and we've seen some of these already. For example, 1 over x is a simple rational function. It no longer has a simple form of, the sum of positive powers of a variable x. It will have possibly negative powers of x, or negative powers of some x minus some linear factor like this, or it might have some other polynomial in the denominator which cannot be factored into linear factors, and it's okay to have something like a form like that. All right. So in general, it will be. So you might have a polynomial in the numerator and a polynomial in the denominator. So that's a rational function. All right. Okay, so Now let's just look at the ones that we've seen before. So we've seen, to review some things we've seen before, our toolkit function, one of our toolkit functions was 1 over x. We saw the graph of that was, it's the inverse function, or the inverse variation function. Y is equal to 1 over x. Okay, so as x goes to infinity, I'll use this arrow notation. Okay. Now the way that we read this, as x goes to infinity, or as x approaches infinity, or this can be, as I said before, it goes to or tends to. Okay, so this arrow means literally approaches or goes to or tends to. So as x goes to infinity, y goes to what value? Y approaches 0. Right? As x gets bigger and bigger, y gets smaller and smaller and tends towards 0. So we have this is now our, this is a different endpoint behavior than the regular polynomial functions. This did not happen for any polynomial function unless the polynomial were 0. And as if it were constant or linear, it would go up, off to infinity, or stay constant. As what happens as x goes to minus infinity, okay, well then y again goes to 0 there. You can see that from the graph. The value of y it's negative all the way in this for x less than 0, but it gets closer and closer to 0 as x gets larger in absolute value, but stays negative. Okay. So I'm just using this arrow notation to make statements about the end behavior of the graph. And that makes it convenient notation to use. What about at other places in the graph? Well, it's also useful to use the arrow notation for points like this at x equals 0, because x equals 0 is not actually in the domain. So we can never really apply, actually get to x equals 0, because if we try to plug it in, we won't get a y. So x equals 0 is actually not in the domain of this function. But we can still describe the behavior in terms of this arrow notation. So we can use arrow notation to describe the behavior of a function near points at infinity, plus or minus infinity, or near points outside of the domain, outside of where the function is defined. So that's one thing about rational roots. Before, for polynomial functions, remember that the domain was all of the real numbers, because every real number can be plugged into a polynomial, and it's just multiplication by real numbers, and then addition or subtraction. Okay, we never had to worry about division by 0, but for a polynomial function, we we do have to be concerned about possible division by 0 because we have a denominator here which might be 0 for some values of x. Okay, so the domain might exclude, well, the domain will exclude points x such that q of x is 0. Okay, so that's the starting point for understanding rational functions and their behavior. So the domain is not now going to usually be all of the real numbers. It'll always have some missing points. Usually we'll have missing points. Okay. And usually also, though, in the regular domain, the function will be smooth. It will be continuous, like I've shown here. Right? So just in this part, it's continuous, and this part is continuous. But right at this point, it's not. There's a big jump there. And we go, in this direction, we go 2 plus infinity. So the way I would say it is as x goes to 0 from the, this is on the right of x, so we go from 0 to, x goes to 0 from the right, or along positive values of 0, or positive values of x. Values which are bigger than 0, that's what I'm trying to say. So x goes to 0, but it approaches along positive values only. Approaches 0 through positive values, or from the right. So that we're moving from the right to the left. Okay, so as x approaches 0 from the right, y goes to higher and higher values. So y approaches plus infinity, we would say. Okay, so this is, again, I'm using the arrow notation to indicate what the behavior of the graph is at a point that is not in the domain. Or, and what's the other thing we can say? As x approaches 0 from the left, which would be denoted by so as x approaches 0 from negative values or from the left, y goes to all the way down to minus infinity. Okay, so there's this is the behavior then. As x comes in from minus infinity, the values of y are very small, close to 0. In fact, they're going to be negative always. And then they'll stay negative and get bigger and bigger, and then finally y will become infinitely negative. It will approach larger and larger values, tending to infinity. Remember, infinity is a larger number than any number that you can think of. So negative infinity is smaller than any number that you can think of. So you just you can keep going closer and closer to that just by, you'll never get there, but you'll get closer and closer as you take smaller and smaller values along the negative side of x. And then when you skip over to here, all of a sudden, if you go in that direction, x gets smaller and smaller from positive values, and goes to 0 that way, and at the same time y goes to plus infinity. So as x goes to you can summarize this in one statement with these two possible cases. As x goes to infinity from the right, y goes to positive infinity. As x goes to infinity from the left, y goes to negative infinity. Okay. So you can actually do this with any point where there's where that point is not in the domain, where you have an infinite, something is infinite either going off to positive or negative infinity. Now at such points, you will have, such as we have here, this vertical line, x equals 0, is called a vertical asymptote. And likewise, the line here, y equals 0, is a horizontal asymptote. So with rational functions, we'll have these vertical and horizontal asymptotes. Vertical asymptote at x equals 0, and a horizontal asymptote at y equals 0. That's a straight line y equals 0. Okay. So an asymptote is a straight line to which the curve will tend to approach closer and closer, but never reach. As as you approach that, as the x value approaches that point, in that, oops. Well, okay, I should be clear about that. So you might have a situation here where you can have several vertical asymptotes. Now we'll see in a rational function you only have one. If you do have a horizontal asymptote, there will only be one. But you can have as many vertical asymptotes as you like. So as you approach, as x goes off to infinity, let's say that asymptote is y equals 0. Oops. So here's my y-axis. So suppose that function approaches as y goes to 0 as x goes to plus infinity. Okay, but near this asymptote, you might go up like this. Then it might come over here and it might do something like this. So it might skip over from y equals plus infinity here to minus infinity and then come down. And then it might cross the x-axis. But that's the horizontal asymptote. So yes, there is a point. It could be points where the horizontal asymptote gets crossed by the curve somewhere in the middle. But it's the endpoint behavior that's really being discussed here. So the asymptote really means that here would be the rest of the curve. There's only one asymptote, always, horizontal asymptote only. And it's saying that at the endpoints, as x goes to plus or minus infinity, then y goes to 0 in both cases. Here it goes to 0 from above, here it goes to 0 from below. So as you get farther and further, as x goes closer and closer to minus infinity, or further and further away in the negative direction, then this curve gets closer and closer to the graph from below. But here it will never touch it. Likewise, here it will never touch the graph. here in the middle somewhere, yes, it did cross and touch the graph. It did touch this asymptote. Okay, so such points will be does not exclude this from being an asymptote. I just wanted to understand that. However, this crossing will never happen on a vertical asymptote, because the vertical asymptote, if it crossed, then that point would actually be in the domain, and that's we'll see as a point which cannot be in the domain. If you have part of the curve, this will also violate the functional property, because we'll be able to draw a horizontal line and cross, or a vertical line we'll be able to draw and cross at more than 2 points, 2 or more points. Okay, so that will fail the vertical line test at least for a function. Okay, so we can cross a horizontal asymptote at finite values of x, but not for a vertical. But a vertical asymptote cannot be crossed. Okay. So, another example. Y is equal to, this again is from our Chilkov function, 1 over x squared. So what that looks like is, it's always a positive number. Again, x cannot be equal to 0, so this point is excluded from the domain. Oops. Y is up here. All right, and as x goes to plus or minus infinity, y goes to 0 from above in both cases. And as x goes to 0 above or below, y goes off to plus infinity. So here again we have a horizontal asymptote where y approaches 0. So the actual asymptote is given by the line y equals 0. Okay. And the vertical asymptote is given by x equals 0. Now it turns out that the vertical asymptote does not, it's approached by the curve from 2 different directions, and always going along just one axis. So it doesn't actually get approached going in this other direction. That's okay. We still regard it as an asymptote. It's a valid asymptote. Okay. We'll see later that this is also sort of a one-sided asymptote. The exponential growth functions and the logarithmic functions also have these one-sided asymptotes. They only are approached on one side. That's fine. These asymptotes are all, by the way, approached from both sides and going off to in both directions as well. They're being approached. All right. So let's move on into particular other examples. Okay, so now we have possibility. So our third example here, this being number 2 and this 1 over x being number 1. We'll try this one, x minus 3 over x squared minus 9. Okay, so what we do is always, it's a good idea to factor both the numerator and denominator. And we'll see why very shortly. It's just that if you want to find all of the zeros of the rational function, those are points where it will cross the x-axis. Like right here, this will be a 0 of the numerator. The numerator is what gives you all the zeros. And the denominator will give you, let's say, all possible zeros. The denominator, when factored, will give you all possible places where it could vanish, which will give you points not in the domain, and which will be possible places where you have vertical asymptotes. Okay. The numerator, so the denominator gives you the vertical asymptotes and the points not in the domain when you set it equal to 0. The numerator doesn't give you the horizontal, does not give you the horizontal asymptotes, just the zeros of the whole function. Horizontal asymptotes must be determined by looking at the overall coefficients of the polynomials. So as x goes to larger and larger values, only the first terms in each polynomial contribute, all the rest can be ignored, and you get a ratio. And that final ratio will simply be a power function, and that will tell you whether your asymptote is y equals 0, whether it's y is equal to constant, or whether there might be some other asymptote, like a slant asymptote, and we'll get to that shortly. So it's a good idea to factor the polynomials right away as much as you can. And now we do that, and now we see we have two factors in common, one in the numerator that's the same as one in the denominator. Now, we can just cancel that, can't we? Yes, we can, only if, though, this factor is not 0. So x must not be 3. Well, another thing we have to restrict, we have to take all the zeros here. So x cannot be 3, nor can it be minus 3. So those are both disallowed because they would make us in a situation we're dividing by 0. We don't want to be in that situation. Okay, so we have to exclude both values from the domain. Okay, well if we do, then this factor is non-zero, this factor is non-zero, we can simply cancel them. Okay. Now, notice that if we just looked at this function, we wouldn't even think of canceling. We would cancel, of course, minus 3, but we wouldn't even think of canceling 3. Why? Because that doesn't make the denominator 0 here. But we still have to exclude 3. Why? Because our original function did have that factor in it. So such a number, it looks like an artificial restriction here, but it has a name. It's called a removable discontinuity. Okay, so whenever you have a cancellation of factors like this, there's the possibility that you have this removable discontinuity. From cancellation of, so it possibly comes from cancellation of factors in a rational function. Okay, so let's see what this looks like. If we plot this, for all the points besides x equals 3 and also minus 3, you get a function 1 over x plus 3. Now this x equals minus 3 does correspond to an asymptote, a vertical asymptote at x equals minus 3. Why is that? Well, you can think of putting in numbers. As you put in values of x which get closer and closer to minus 3, this whole thing will get closer and closer to 0. If you put in values which are, for example, bigger than minus 3, so they're positive, so slightly bigger than minus 3 means they're bigger than minus 3. Okay. Then, if you add 3, you'll get something positive. So this will be 1 over something positive, which is getting very small in the denominator, so the number will be getting huge in the overall. So it'll look like this. Okay, and as x goes to plus infinity, it'll go closer and closer to 0. Maybe I need to make it a little bit further away from the asymptotes at this point, so it's sort of like more like this. Now at this point, I get a hole there, because it's not in the domain. So this just simply means that point is excluded from the graph. Now on the other side, I get, if I take x, so this here, y goes to plus infinity. As x approaches minus 3 from the left, from smaller values, that's what this means, then it's bigger in absolute value, so I'll get a negative overall, small negative number in the denominator. And so y will go off to minus infinity. So it'll look like this. So this is an asymptote, a horizontal asymptote. Here's a vertical asymptote. And so without this hole here, this would just be the graph of 1 over x plus 3 by itself. I've excluded x equals minus 3. That's the horizontal, the vertical asymptote. And this is my removed point or hole. Hole in the graph. Okay. Now I can recognize the this graph, I can recognize this as 1 over x, our toolkit function, where I've shifted everything over to the left because I add 3. So I shifted all over to the left by 3 units in the x direction. Right? So that's just taking, that will also shift the vertical and the horizontal asymptotes as well. Well, actually, it doesn't actually change the horizontal asymptote because I'm shifting it along itself, but it does shift the position of the vertical asymptote 3 units over. So it's just the graph of 1 over x, but shifted over. So that's how I can very readily and quickly draw this graph. And just establishing a point which makes it easier. If I draw a minus 2, for example, then I should get 1. Okay, so this point 3 is going to be at 1 over 6. Because if I could plug that in, I would get just 1 over 6. Okay. Okay, so these are just some examples of rational functions. Okay, so in general, let me just look at my list of problems here we can try. So the examples will give you a few more things to try here. Like for example, we could try at 4. Find the domain of f of x is equal to 4x over 5 times x minus 1, x minus 5. Four x over 5x minus 1 times x minus 5. That's staying in. Okay. All right. So now the rational function here is fortunately already in factored form in both numerator and denominator. So it makes it easier for us to find the domain as well as a number of other features. Okay, so immediately we can see that. So first we should factor numerator and denominator, then we should cancel any common factors if they are there. All right. And the domain should be the original uncancelled, obtained from the original uncancelled factors in the denominator as well as, so you would start with all the original factors in the denominator before cancellation. So you set the denominator equal to 0, and so you get x equals 1 or x equals 5. So these are the roots, so that means the domain cannot include those. So the domain is equal to all the real numbers, and except for 1 and 5. So I've subtracted off 1 and 5. Or you could write it as an interval notation, minus 1 all the way up to 1, not including, and then continue on the other side from 1 to 5, not including either 1 or 5, and then union. Again, 5 is not included. So these will be all the real numbers except 1 and 5. All right, just the same as I wrote here. Okay, so now how do we consider graphing such polynomials? Okay, so we want to graph them by looking at all possible features. So those will include features like the zeros, the vertical asymptotes, the horizontal asymptotes, and possible removable discontinuities like this. All right. So intercepts, x and y intercepts, those are the same as the zeros. There's a y-intercept. Sometimes, not always, is there a y-intercept. Why? Because if x equals 0 is in the domain, which it will be here, it's right in here, this interval, then you will have a y-intercept. So the y-intercept is simply y f of 0, the ordered pair. Okay, so there's only one of them if it exists. And it only exists if 0 is in the domain of f. Okay, if 0 is not in the domain, then you don't have a y-intercept at all. If and only if. Well. Okay, so that covers the case of y-intercepts. X-intercepts are obtained by setting the numerator equal to 0. And one should remember that to check to see if we had a cancellation. If there is a cancellation of a similar factor from the denominator, then that would mean that x equals 0 is not in the domain. So that wouldn't actually be an intercept. So you'd have to exclude that point, draw a circle there. Okay, so we look for the horizontal asymptotes, vertical asymptotes, the zeros, the y-intercept, the x-intercept. Okay, now we discussed a little bit about vertical asymptotes. You obtain them by setting these factors after cancellation to 0. So before cancellation, that's how you get the domain. After cancellation of common factors between numerator and denominator, then you again set the denominator equal to 0, and that will give you all the vertical asymptotes, equations of the vertical asymptotes. Like here they will be x equals 1, x equals 5. Okay, so that part is straightforward enough. So let's just write it like this. Before cancellation, our factors set denominator equal to 0, and that gives us domain. Or explicitly, points that are not included in the domain. So that's one point. And then after cancellation, again, the set denominator equal to 0. And you get the vertical asymptotes. How about the horizontal asymptotes? Let's look at that. Okay, so there's three possible situations here. One situation, so you look at the leading terms. So you have a, say, nth degree polynomial upstairs in the numerator of this form, which is the form I've usually written it. And you have, let's say, bm, x to the m. So the degree of this one is n, and the degree of this one is m. an is not 0 by definition because the degree of this is defined to be n, and bm likewise, the m is not equal to 0. So n and m are fixed numbers, and the remaining factors may or may not be 0. The remaining coefficients may or may not be 0 here. If not, then they should be included here. Okay, so what as x goes, this asymptote is approached as x goes off to plus infinity, or x goes to minus infinity. So x gets large in absolute value. All right, when x gets large in absolute value, these leading terms will always get bigger than any smaller power. Why? Because this will have, say, 3 powers of x. This will already have 3 powers of x plus 1 or 2 more. Well, the 3 powers will make this grow just as fast as this one. Eventually, this will overtake this one, no matter what coefficient I have here. This might be a big, big coefficient, but x can be made to be bigger than that one. so that an times x will be bigger than this number. So if this is negative, then, or positive or whatever sign this is, this absolute value can be made bigger, and this will eventually dominate this. So whether this is positive or negative will eventually mean that the whole thing will be positive or negative. And it will just rely just on the first term. So as x goes to larger and larger values, or as x goes to negative values larger and larger, we'll end up with just the first two terms, one in the numerator, one in the denominator. And this will just be a power function. an over bn is the factor that comes out front, and then you have x to the power of n minus n. So this could be a positive, 0, or negative exponent. If it's, so the simplest maybe would be when they're equal, when the degrees are equal, then n equals m. Okay, then you just get the constant an over bn. That's not going to be 0, right? Because neither of these are 0. So this is what the function tends to. That will be this line. So it's going to be some line different from the x-axis, positive or negative. We don't know. It's not going to be 0 though. So it's just a horizontal line. So we have a horizontal asymptote here. Equal to the ratio of the two coefficients. N equals m, so really this is going to be n as well. That's case 1. Let's try case 2. N is less than m. Well, in that case, y is equal to an over bm. And then this thing will be 1 over x to the m minus n. So this will be a negative power of x, and it will go to 0. This whole thing will go to 0 as x goes larger and larger. In both the positive and negative directions. So this again is a horizontal asymptote. Up here it was a constant, not equal to 0. Here it's simply y equals 0. Now finally 3 could have n bigger than m. So then you have this power law behavior where this is a positive integer, positive whole number. Okay, so this could be quadratic, this could be cubic. All right, so that's not going to be really a simple asymptote. It's certainly, if this difference is 2 or greater, then it's going to be some curve, quadratic or cubic or higher. So it's not going to be a straight line. Only if this is equal to 1 will you get a straight line. In that case, so n in that case is just 1 bigger than m. That will give you what's called a slant asymptote. Okay, so let's do a simple case of that. Y is equal to x squared plus 1 over x. All right. So let's see what this looks like. So if we simply divide this, we get x plus 1 over x. So I take the factor and divide it into the first term, and I get x. Take the factor and divide it into the second term, I get 1 over x. Excuse me. So if we let x go to larger and larger values, this term here, 1 over x, gets very, very small compared to x. So this will go to 0. And this will go off to plus or minus infinity, but in just the way that the straight line does, y equals x. So this is my slant asymptote. Okay, so we draw that in here. Say it as a dashed line to show that it's not part of the function or the graph of the function, but the graph of the function will approach that line as x goes off to infinity. Okay, notice one thing here. This goes off to, as x goes to plus infinity, this goes to 0 from positive values. The whole thing goes to 0 from positive values. So we remain above the curve, above this line, as we approach it. So it looks something like this. What else can we say about this graph? As x approaches 0 from above, from positive values, then y goes to, you can easily see that point is excluded from the denominator. There's no common factor in the numerator which will cancel it, so that's a valid asymptote that's vertical. So it'll look like this. Y goes to plus infinity. So it'll come, as it approaches 0 from the right, it will go off to, y goes off to plus infinity. So it will look like this. So somewhere in the middle, they will join. Okay, so you get some sort of it's a function, so this does not curve back on itself. It goes closer to this line. It doesn't violate the vertical line test. It doesn't fail the vertical line test. So you have something like this. Now this is also an odd function. Because if you plug in minus x, this will stay the same because it's actually an even polynomial here, and this will be an odd polynomial, so this will change sign. Plus and a minus give you an overall minus sign. So it will be an odd function according to our regular definition. So if we just reflect this about the origin, then this will give us the other side. Okay, so that's what this function looks like. This point will be the same values of x and y as the negative of these values of x and y. Okay, so this will be a rectangle here if we draw this up close together. Connect these lines. And the center of this rectangle will be at the origin. Okay, so that's an example of a slant asymptote. Generally, to get a slant asymptote, it's not sufficient to just take this and substitute n minus m equals 1. That will give us the leading coefficient. But there will be a constant term here which is not given to us by just this simple rule. So a slant asymptote, you want to get the full line to which the curve actually tends. And you actually get it by synthetic division. Okay, so let's see how that works. In this case, 1, 0, 1, 0. And we get 1, 0, 1. So that means that we have x, remainder 1 divided by x. So that's just what we had before. So these two coefficients give you the full equation of the line for the slant asymptote. Here we see it's just x and 0, so the y-intercept is in fact 0. And I've tried to draw that, but it actually goes through 0. But you might have situations like this, x squared over x minus 2. Then you have a vertical asymptote now at x equals plus 2 like this. And you're obviously going to have a slant asymptote because the numerator has a degree 1 greater than the degree of the denominator. So you're satisfying this condition. But if you just take x, the line x, then you won't get, as x approaches from above, 2 from above, you go up to plus infinity, right? And then as x gets greater and greater, you'll go up like something like this. So the line will actually, you might not go through the origin. So just taking it to be x would be wrong. So, but use synthetic division. And then you put in your 2, and then you get your 1, 0, 0. Right, because that's coefficient of x squared, that's coefficient of x, that's the constant term. So you get 1 times 2 is 2, add it and you get 2. Times 2 is 4, add and get 4. So the remainder will be 4, but that will be divided by 4 over x minus 2. And as x goes to larger and larger values, that will go to 0. Okay, so that will go to 0, and then the rest will give you the equation of the line of the slant asymptote. So it will actually be the line going through plus 2. It's actually not the way I've drawn it here, apparently. So it looks something like this. So it's actually turning way up here, going up like this. And what about down here? Oh, okay. So as x comes in from minus infinity, then this will come in from, y will come in from minus infinity. And I'll get a value which turns around somewhere. I actually have to go through x equals 0 somewhere and then go down like this. So I've drawn it, maybe the, I'm not sure if that's correct or not, maybe the maximum, the local maximum here. You can see there must be a local maximum and local minimum. Maybe that happens at x equals 0, I'm not sure. It might go through it and then come above a little bit and then go down. So one might check that. I'm not sure if it goes through 0. But this is what the graph should look like then. Okay? So in order to check this out, I might think of shifting it. So maybe it's a shifted version of this one. Okay, so you might want to check that out. In any case, I've gone a bit over time, and so I'll continue this discussion of rational functions and graphing rational functions next time. And with that, pretty much want to wrap up the 5th chapter and move on to exponentials and logarithms, chapter 6. Okay, so again, any questions, please let me know. Thank you for listening to this lecture. Have a great day.